Hi and welcome to this third video of my playlist about the preparation of Benzaldehydes. This video is about the preparation of Benzaldehydes from methyl arenes. This strategy is most relevant for the industrial manufacture of aldehydes, and the reaction conditions are often too harsh to be compatible with highly functionalized starting materials. However, some selective procedures exist that are suitable for laboratory preparations of sophisticated intermediates. There are several strategies for preparing Benzaldehydes from methyl arenes. One is the direct oxidation, for instance by air or hydrogen peroxide and some catalyst. I'll show you specific examples in a minute. Alternatively, methyl arenes can often be halogenated selectively at the benzylic position by radical chain halogenation. These reactions usually require some radical starter or UV light. 2- or 3-fold halogenation are common side reactions. The resulting benzyl halides can be oxidized to aldehydes with a number of reagents under milder conditions and often with higher selectivity than that achievable by direct oxidations. Then, dihalomethyl arenes, also called Benzaldehydes, have the same oxidation state as aldehydes and can be converted into the latter by simple hydrolysis. I'll show you some examples later. Nitrotoluenes and other methyl arenes with acidic methyl groups can sometimes be oxidized by intermediate oxime formation. Usually, these reactions work best in the presence of bases, as sketched here. The initially formed nitrosomethyl arene tautomerizes to an oxime, which can then be hydrolyzed to the aldehyde. If the methyl group is very acidic, oxime formation may also occur under acidic conditions, just like the diacetation of an aniline. Benzaldehyde is mainly used as flavoring agent and as synthetic intermediate, for instance for the preparation of benzyl alcohol, benzylamines and cinnamic acid. It is obtained as byproduct of the oxidation of toluene to benzoic acid. Benzoic acid is produced on a large scale, approximately 500,000 tons per year, mostly as a starting material for caprolactam and phenol. Thus, the amounts of benzaldehyde obtained as byproduct are, as far as I could find out, enough to satisfy the current demand. The oxidation conditions can, however, be modified to increase the ratio of benzaldehyde. This here is a typical oxidation by air in liquid phase, catalyzed by cobalt acetate and sodium bromide. When optimizing such reactions, one must take care to remain outside of the explosion limits of air-toluene acetic acid mixtures. Unfortunately, this is often forgotten, and explosions during the development of oxygen-mediated oxidations are common. Benzaldehyde can also be manufactured by 2-fold radical chlorination of toluene and hydrolysis of the resulting benzyl chloride. This requires dedicated equipment for photochemical chlorinations. I'll show you later some examples of more laboratory-friendly variations of this strategy. Let's begin with specific examples of direct one-step oxidations of methyl arenes. A safer strategy than the use of oxygen is the tempo-catalyzed oxidation with hypochlorite. In this example, cobalt acetate was required as co-catalyst and the oxidation already proceeded at 0 degrees Celsius. Also, oxidations with hydrogen peroxide are safer than aerobic oxidations. Here, cerium acetate and sodium bromide were the catalysts and the oxidation was conducted in acetic acid. Along with the aldehyde, a small amount of benzylic bromide was also obtained. 2 or 4 methyl phenols can be oxidized to hydroxybenzaldehydes in high yield, but special conditions are required that are not usually applicable to other methyl arenes. 2 and 4 hydroxybenzaldehydes are vinylogous to formic acid and surprisingly stable under alkaline conditions. In the example sketched here, the phenol was oxidized by bromine formed from a mixture of hydrogen bromide and hydrogen peroxide. No arene bromination occurred because the ortho and para positions were blocked. Here, paracresol was oxidized just by heating with palladium on charcoal under alkaline conditions. No Cannizzaro reaction of the product occurred, because, as mentioned, deprotonated 4 and 2-hydroxybenzaldehydes are much less reactive than benzaldehyde. Another user-friendly oxidant is terz-butyl hydroperoxide. In this example, nitrotoluene was oxidized to an aldehyde by this peroxide and 10% of a cobalt-2 complex in acetone. I'll show you now some examples of benzylic halogenations and oxidation of the resulting benzylic halides. Sulfuryl chloride is an inexpensive electrophilic chlorinating reagent that can be used as an alternative to elemental chlorine for radical chlorinations, as shown here. The radical starter was AIBN and the solvent chlorobenzene. Although there is some structural similarity between sulfuryl chloride and phosphorus oxychloride, sulfuryl chloride cannot usually be used as activating reagent in the Wiltzmeier reaction. Only very reactive arenes can give aldehydes upon reaction with DMF and sulfuryl chloride, but usually arene sulfonyl chlorides or chloroarenes will be obtained. A number of different reagents can oxidize benzylic halides to benzaldehydes. One practical, environmentally friendly reagent is aqueous nitric acid. In this example, refluxing for 5.5 hours gave a high yield of the target aldehyde. No over-oxidation or aromatic nitration occurred. Also, amine oxides can selectively oxidize benzyl halides to benzaldehydes. Here, the reaction was conducted in refluxing THF and gave an almost quantitative yield of aldehyde. Amine oxides can also be generated directly in the reaction mixture from a tertiary amine and hydrogen peroxide, as in these two examples. To prevent quaternization of the amine, its oxidation should be complete before addition of the benzylic halide. Both electron-deficient and electron-rich benzyl chlorides were oxidized in high yield. In the so-called Kornblum oxidation, alkyl halides or sulfonates are heated with DMSO and a weak base. O-alkylation of DMSO yields the same intermediate that is formed during Swern oxidations. In this example, a 1,4-diformylbenzene was prepared by twofold oxidation in DMSO as solvent and with a large excess of sodium bicarbonate. Radical brominations are more expensive but easier to perform than radical chlorinations and are therefore often preferred in small-scale laboratory preparations. In this example, paraxylene was first brominated with NBS and AIBN, and the crude benzyl bromide was then oxidized by heating with an excess of amine oxide. The first equation on this slide is again a typical radical bromination by NBS with benzyl peroxide as a starter. The resulting bromide was oxidized with urotropine, the condensation product of ammonia and formaldehyde. Because of its cage structure, urotropine is a strong nucleophile, almost as powerful as DAPCO or quinoclidine. The initially formed benzylic amine was then oxidized by formaldehyde or some formaldehyde-derived iminium salt to the final product by a mechanism similar to the Oppenauer oxidation. Another suitable oxidant for benzylic halides is 2-nitropropane. Benzylation of the nitronate anion at oxygen yields the intermediate shown here, which then fragments into an aldehyde and acetone oxime. Let's move on to the hydrolysis of dihalomethyl arenes. Many high-yielding procedures have been reported, and I've listed here some of the more practical strategies. Both acidic and alkaline conditions can be used, but benzaldehydes are usually more stable under acidic conditions, and acid-catalyzed procedures should therefore be tested first. In the presence of strong bases and water, Cannizzaro-type disproportionation can occur, and electron-deficient benzaldehydes may undergo nucleophilic deformylation. In this example, both methyl groups of a chlorinated metaxylene had to be converted into formyl groups. This was achieved by solvent-free 4-fold radical chlorination with gaseous chlorine and AIBN as a starter. The main product was the desired Benzal chloride, but around 10% of some byproducts were also formed. Hydrolysis of this product mixture with concentrated sulfuric acid yielded the target dialdehyde in 82% overall yield. This is how well-optimized procedures should look like. No solvents, no expensive or dangerous catalysts or reagents, unproblematic waste streams, and a good yield of the final product. In this example, the hydrolysis conditions were a bit milder than in the previous example, to prevent saponification of the ester and halogen exchange reactions. Refluxing in formic acid gave the required benzaldehyde in 73% yield. Some benzylic halogenations succeed even without UV light or radical starter. In this example, 4-tertsbutyltoluene was brominated twice at the methyl group just by heating with bromine to 170 degrees Celsius. Hydrolysis to the aldehyde was achieved under alkaline conditions, with urotropine and 3% of sodium hydroxide. When mixing urotropine with electron-rich arenes, as the one of this example, it is important to keep the reaction conditions alkaline to prevent acid-mediated aminomethylations of the arene. With phenols or anilines, however, hydroxy or aminomethylation may even occur under basic conditions. Also, pyridine can be used to hydrolyze Benzal bromides. Here the starting material contained an ester and an acetal, but still a good yield of the aldehyde was obtained. Toluenes with particularly acidic methyl groups can be oxidized by other methods than less acidic toluenes. Reaction of 4-nitrotoluene with sulfur, for instance, gives a high yield of 4-aminobenzaldehyde. Because of the sulfide required to initiate the reaction and formed during the oxidation, reduction of the nitro group by sulfide could not be prevented. Another way to oxidize strongly acidic methyl groups is by nitrosation to an oxime, followed by hydrolysis. Nitrotoluenes, for instance, can be transformed into oximes by treatment with alkyl nitrides and an alkoxide, as shown here. This here is another example of oximation of a nitrotoluene. Potassium alkoxides sometimes give better yields than sodium alkoxides, and some optimization may be required to prevent oligomerization. The hydrolysis of aldehyde-derived oximes is not always easy, because nitriles are readily formed. This here is an example of an oxidative strategy which gave good yields of aldehyde, but also some benzoic acid as byproduct. In this example, acetone was used to trap the hydroxylamine. Unfortunately, the reaction took 5 days, what is a bit too long. No extensive hydrolysis of the cyano group occurred. So, what are the potential side reactions? In the presence of alcohols or water, aldehydes can form hemiacetals or hydrates. These are strong hydride donors and can be readily oxidized to carboxylic acids. Then, as mentioned, the hydrolysis of oximes can give nitriles as byproducts. And radical halogenations can yield a large number of byproducts resulting from the halogenation of functional groups or of the arene. Here are some further references which you can also find in the description of this video. The next video of this playlist is about the reduction of various benzoic acid derivatives to aldehydes. This includes the Rosenmund hydrogenation of acyl halides and the reduction of nitriles, amides and esters. So long.